we'll officially get started. I have the pleasure to introduce Alastair Craw from Bath, who's going to be telling us about what is the Hilbert scheme of points in the plane. Please take it away, Alex.
Hey, thanks. Thanks to Yang. And like yesterday, I was at the talk that Al gave. I too have taken Yang very much at his word to try to be really very accessible. So the first title and abstract I sent to him, I got the sense that he was a bit shocked. So I watered it down, found a more general, friendly approach. And I want to tell you something that should be very, very well known. I know that many people do know this, but it's a point of view that I think makes this really very accessible to understand what is the Hilbert scheme of points in the plane. And then towards the end of the talk at this time, I'll say a little bit about some recent work I've done in understanding the Hilbert scheme of points on an ADE singularity. So that is the quotient of the plane by a finite subgroup of SL2. But since I want to talk about the Hilbert scheme of points in the plane, we've got to start in understanding what a point is. And this sounds facetious, but of course in algebraic geometry, we have a slightly unusual notion of a point. Right, so of course, to start with, a point in the plane should just be a pair of elements in whatever field we choose. I'm going to denote this K, but of course this sometimes in examples, I guess I'll typically use C. But so a point on the first approximation is just a pair of scalars, so an element in two-dimensional vector space. However, we as algebraic geometers are very much interested in the functions or the polynomial functions that cut out that point. And we insist that our point remembers the functions that cut it out. And so we're going to have to record that data. And I think it's really worth, very, very down to earth, looking at the origin in the plane over the complex numbers. So of course, if I choose coordinates, X and Y, and look at polynomials in X and Y, then of course, if I say X equals 0 and Y equals 0, then I cut out the origin. Yes. So that's the origin that everyone would tell us in, say, high school. But of course, I can also cut it out by looking at the vanishing of X cubed and Y. Then, of course, I've got a little bit of extra tangent and higher order information. Or I can just be a little bit fancier and set some higher order things. And of course, there are infinitely many ways to do this as I gradually increase the exponents on the monomials that are in my defining equations. And that's only for the origin. And the point is, these three, or indeed the infinitely many variants of this that you can set up even for the origin, we want to distinguish between all of these different versions of the origin. So how do we do this? And let's also stay down to earth for a moment. So let's look at a formal power series in two variables, X and Y. And so let's expand such a thing. Now, for each of these points, I want to help me distinguish them, not to entirely distinguish them, but to help, I'm going to introduce the notion of length. And for the moment, let's just look at the length of a point at the origin, one of these guys we've looked at. So if it's specified by a collection of polynomial functions, and then since I'm looking at the origin, let's for the moment assume it's specified by monomials, as these three examples are, then all I'm going to do is substitute each of these X equals 0, Y equals 0 into this formal power series, and then see how many variables are left. And the number of variables that are left is going to be the length of that point. Okay, so in the three examples we looked at, yes, if I choose X and Y and I set them both to 0, then of course all of these guys disappear and I'm left only with A. There's one variable, so we say it has length 1. If I set X cubed to 0 and Y to 0, well, X cubed is going to be out here. If I set Y to 0, I'm killing this, this, and this, but I still have these three options that has length 3. And I claim, but feel free to draw a wee picture to convince yourself that this X cubed, X squared, Y, and Y to the 4 vanishing gives a point. It still gives the origin, but that has length 13. And the point I'm, pun not intended, the point I'm moving towards is exactly that rather than thinking about the set cut out in the plane, we should really be thinking about the ideal of polynomial functions that vanish at the point, or the ideal of functions that give birth to that point, or more specifically, the quotient ring. The quotient of all polynomials in two variables modulo that ideal, and the ideal might be that generated by x cubed and y, as it is in one of the above examples. But this is the thing that we care about. And a collection of functions, as in this case, this pair, that defines a point precisely when this vector space has finite dimension. And it's the dimension of that vector space that we've been calculating up here in doing these calculations. So for a point, I want that to have finite dimension. Indeed, that finite number is the length of the point. So this quotient ring, as a vector space, it has dimension 1, 3, and 13 in these examples. So points come with all this extra data. Indeed, a point really is this information. And this then allows us to set up the definition I'm gunning for. So now that we know what a point is, the Hilbert scheme of, so let's fix an n. So then the Hilbert scheme of endpoints in the plane is, at least as a set, it's this. It's the collection of ideals for which this vector space has dimension n. And since we're insisting it has finite dimension, then each of these defines a point. So you can think of this either as the collection of points for which this that have length n, that's one way to do it, or as the collection of ideals, or indeed as the collection of these quotient rings. So 3 different ways to see it, all of which are equivalent. But the point is, this is just a set, the way I've introduced it to you. And but yeah, at least it's non-empty. And let's make 2 points with different examples. So yes, it's non-empty. If we fix an n, then choosing this ideal, let's have all the higher powers of, or all powers of y vanishing, but just truncating x to the n. My power series survives with n free variables. So sure enough, I have at least 1 point in this Hilbert scheme. Secondly, so that's so at least these are non-empty sets. And let's do another sort of silly observation. So let's just take n equals 1. If I want my quotient ring to have dimension 1 as a vector space, then sure enough, this is a field. So the ideal I is maximal, and Hilbert-Schnell-Stellensatz, and that's why I'm working over the complex numbers here, tells us that the ideal has this form. And that's where we get our P and Q from. So sure enough, for n equals 1, a point looks like the kind of point that we would have defined when we were in high school. And that being the case, the Hilbert scheme of 1 points is the plane itself. So let's face it, that's not very interesting. But we do at least know what the Hilbert scheme of endpoints is as a set. So now I want to define this Hilbert scheme as an algebraic variety. And I reckon the first geometric construction, once you've taken on board that we are trying to parameterize things that look like this. And that's why I've spent a bit of time discussing that. Once you've taken that on board, I think the construction is actually really quite intuitive. So that's what I'm going to try and convince you of now. So I hope I've convinced you, or at least proof by intimidation, that points really are, well, vector space. Yes, this is a vector space, but it's more, of course, it's a finitely generated K algebra. But in particular, this is a vector space of dimension n, but it's more. And the key point for the construction, or the first really key point, is each one of these vector spaces, yeah, it's not just a vector space, it's actually a module over the polynomial ring in 2 variables. And in particular, anything, any representative in our quotient ring, we can multiply by x and by y in a way that's compatible, by which I mean that x, if I have a function and I multiply by x and then y, then I get the same thing as multiplying by y and then x. And again, let's stay very down to earth, just to be really concrete. Let's look at one of our a slightly different point at the origin. So of course, I'm talking about the 0-dimensional scheme when I say point. So at the origin, I'm interested in the point cut out by this ideal, and truncating our power series in 2 variables leaves these 4 variables, a, b, c, d. And if a general function in this ring looks like this, then yes, I can multiply it by x, and I can multiply it by y. And this determines our module structure as well, of course, with scaling. And just to notice the point that in this case, if I multiply the top line by y, then in fact that piece will disappear because y squared is 0. So I'd be left with ax times y. And on the bottom line, if I multiply by x, then x squared would appear here, that would disappear, and I'd be left with a times x times y. So again, xy times a function is yx times a function. So x and y commute in this multiplication. So this is where I've been going so far. What is a point in the plane? Well, yes, of course, it's a quotient ring K of xy modulo some ideal that has finite dimension as a vector space. Or equivalently, the actual data we've got there, first of all, it's a vector space, V0, and that might be, I mean, we're interested in specifying that to have dimension n for some fixed n. The other piece of information I've just discussed are the two maps from the module structure. So I can multiply that vector space by x, or to give me an endomorphism of the vector space. I can do the same thing by y, and as I've been trying to illustrate, of course, these multiplications commute. And there's one extra piece of data here, that namely it's the specifying an element in V0 that's going to play the role of 1, or really 1 modulo I in this quotient ring. Because once I've got 1, then I can let x act to work out what x is, and let y act, and then so on, to gradually let x and y act to build up a basis of the entire vector space V0. It's that specifying that particular element 1 and letting the K of x y module structure then determines the structure on the whole thing. So that's a point. All this data here is the information of a point in the Hilbert scheme of n points, at least if this vector space V0 has dimension n. And so let's visualize this. So this remark that this third point, to specify, of course, a vector in V0 is the same thing as writing down a non-zero map from a one-dimensional vector space, where, of course, the vector is being picked out by the image of the scalar 1 in our field. And so if that being the case, all this information I can specify, or much of it, in this little picture here. I've got my n-dimensional vector space. I've got maps that I think of as multiplication by x and multiplication by y. I'll keep those on. And then this extra information about part 3, if this is a map, let's call it I, from the field to V0, I want that to be non-zero in such a way that the image of 1 generates the whole thing, the whole of V0 as via these maps x and y. So the module structure then fills out the whole of V0. Right, so this is the point I meant, that when I apply x and y repeatedly, I generate the whole of the vector space V0. So this picture really encapsulates what we mean by a point in the plane of length n. And our goal then is to parameterize all possible points of length n. I want to parameterize all possible pictures, and to do that, and it's possible to do that, let's first of all choose a basis on V0. So V0 now becomes, of course, just my n-dimensional vector space. And I've got these maps. Let's give them some names. So B1, B and B2 for the, now they were maps, well now they become just n by n matrices. And a map that's an n by one matrix for the linear map that picks out this element 1 in our vector space V0. And all this information I can encode. I know all possible maps, just a collection of matrices. And so I'm interested in parameterizing triples, right? So I want to record B1, B2, and I. B1 and B2 are both n by n matrices, and I is an n by 1 matrix. And I remind you that since x and y commute, I'm going to ask that B1 and these two matrices commute as well. So the set of all possible data for any of these points of length n is the space Z. And of course this, where are we? So this is a vector space, and I'm cutting out a collection of equations in there. Right? B1 and B2 are both n by n matrices, so I've got n squared equations cutting something out in a vector space. So this is an affine variety, or an affine scheme. But I've not done everything yet. So these two things to note. Firstly, we haven't tried to insist that the image of 1, so 1 in here, its image has to generate Kn as a KXY module. So remember, any quotient ring, K of XY mod I, it's cyclic as a K of XY module with generator 1. So I want, whatever vector we pick out under this map, I want that to generate Kn as a KXY module. That's one thing that we need to encode. It's missing at this point here. And the other thing, we were naughty when we chose a basis for V naught. Right? I'm trying to parameterize this guy. I'm trying to parameterize these things, and I chose a basis. The basis allowed me to write matrices so I could look at everything at once. But of course, I have to remember to mod out by that choice of basis. And in order to do that, of course, I just let the change of basis group act. I let GLN, so the general linear group on this vector space, I let that act, and I should look at orbits under that action. And this is an explicit description of how that group acts on triples. But the point then is that this thing I care about, the Hilbert scheme of endpoints in the plane, should be some sort of orbit space. So I should look at this collection of this set here, and then mod out, or this affine scheme, and I should look at orbits under the action of GLN. But I've got to somehow encode this data as well. And the key to everything is that it's possible to solve both of these problems at once. On the one hand, construct an orbit space such that the only orbits we end up studying are those corresponding to triples satisfying this condition. In fact, this is the first theorem. This is the construction of the Hilbert scheme of endpoints as an algebraic variety. So when I've got a group, a reductive group, certainly GLN, acting on an affine scheme, so I can create quotients using geometric invariant theory if I choose a character of the group. And here I'm giving you an explicit character, right? So characters of GLN, the character group is isomorphic to the integers. A general character is the form det g to some power say theta, say, and I'm choosing theta equals 1. So I'm choosing a character of the group, and what that's going to do is it's going to tell me which parts of Z to throw away before I make an orbit space. And of course, this construction is familiar to us from projective space, that when C star is acting on a vector space of dimension n+1, then we throw away the origin to make a quotient space. Well, sure enough, that's what we're doing here. And it's chi, it's this choice of chi that's determining which parts we throw away. So I'm claiming then that for this particular choice of chi, we construct the Hilbert scheme of endpoints. So let me try and convince you of this. And this is more or less a proof I'm going to give you here. So let's sketch this. That I'm interested in pictures like this. Let's go back up. Pictures, I want all this data. So I've got a vector space K direct sum Kn, and I've got 3 maps on it. And so that information, I'm recording what's called a representation of the quiver. In other words, it's just a vector space, and it's this vector space together with these maps. So I goes from K to Kn, and B1 and B2 go from Kn to itself. And that data, and remember, of course, this we want to specify a point in the Hilbert scheme, that defines a point in here, and therefore it's one of the points we care about when we make this quotient. So that defines a point in there. In other words, it defines a stable point precisely when the following condition happens. So that's that for every sub-representation, so that's the key condition. So I've got this V, and I'm interested in a sub-representation of V. And what this means, this is that I've got, again, this vector space is a subspace of this one-dimensional vector space, and this vector space is a subspace of this n-dimensional vector space. And moreover, the maps in V prime are simply obtained from these maps by restriction. So that's the notion of sub-representation. And the condition, and this was first written down in this context by Alastair King. So for a sub-representation, so V itself is going to be stable, so it's going to be allowed in our club, precisely when this condition that I put in a red box is satisfied. This condition in the red box is actually very easy to understand precisely because this, this guy is a subspace of a one-dimensional space. So we've got two options. If this has dimension 0, then of course that part disappears. And this is a vacuous condition, right? When this is 0, of course the dimension of V0 prime is greater than or equal to 0. It's completely vacuous. So it's only a condition when this has dimension 1. So when that has dimension 1, and indeed we are left with that condition, we're saying that V0 prime, I remind you V0 prime was a subspace of Kn. We see that V0 prime has to be the whole thing. In other words, this map I, let's put this in red. So this map I, and remember that B1 and B2 are here, for every sub-representation, whenever that's non-zero, in other words, whenever it's a one-dimensional vector space, V0 prime has to be the whole of Kn. In other words, this map I, and then all these maps must generate the whole of the n-dimensional vector space. So here's the key conclusion. What we've done by imposing this stability condition, this choice of the character chi, and insist that the only triples I care about, the only quiver representations I care about, are those satisfying this condition here. This corresponds to exactly the condition that the image of this element, in other words, I of 1, generates the entire n-dimensional vector space as a kxy module. And that's the condition that we had a point of length n after all. And so that's why this set is exactly the set of orbits. In other words, the Kn that was sitting in this vector space here, we mod out by GLN, so now it's V0 again. That data is exactly parameterizing the chi-stable triples precisely correspond to points in the Hilbert scheme. So vector spaces V0 of dimension n together with two endomorphisms such that the image under this map I generates the whole of V0 as a kxy module. So that's the proof, that really is it. So previously our Hilbert scheme was a set. And now we've got something sitting in algebraic geometry. We've got a GIT quotient, so this really is an algebraic variety. And now I want to say that we get lots more for free. So we've just described what I think is quite an intuitive description of the Hilbert scheme of endpoints. And I'm now going to repeat the construction with a difference, and I'm going to throw in one extra arrow. So take this on trust for the moment. I'm just going to do something. I'm going to repeat the construction, but just ever so slightly different, where I throw in a map J going in the other direction from Kn back to K. So we've not got triples, we've got quadruples, and we look at the space of all possible quadruples, and here it is. So this is a vector space, and now I'm input, it's still one condition, but notice that the condition differs slightly on the right-hand side. Rather than being 0, I'm insisting this is minus ij, by which I mean j follows, I follows j. So I'm insisting rather than b1 minus b1, b2 minus b2, b1 being 0, it's the composition of these two maps at Kn. This again is some sub-scheme of this vector space. GLN acts, again, I can choose exactly the same character as before. And there's this really, really cute result. Thing to note, that if I have a quadruple, if it's chi-stable for exactly the same character as before, it turns out that adding this map J did absolutely nothing at all. It's the 0 map. And in particular, if it's the 0 map, I mean, we're effectively dealing with something in Z chi-stable. In other words, a point that we were considering before. So this little lemma tells us that, and notice, of course, when J is 0, the equation recovers the equation we had previously, right? That disappears to 0. And so exactly, we've got an inclusion map from the chi-stable locus in Z to the chi-stable locus in W. It's just this very, very concrete map. This is actually an isomorphism, and more than that, not just of affine schemes, but of GL equivariant or of GLN schemes. The point being that the GIT quotients are the same. Okay, so we've got a ever so slightly different way of viewing the Hilbert scheme of endpoints in the plane. Namely, we can throw in this extra arrow if we wish. What do we gain from that? Well, let's pause just to define notions. So for this quiver with this extra arrow going backwards, and for these choice of dimension vectors, so I put n at one, kn at one vertex and k at the other vertex, and for exactly the same characters before, chi, then we have this guy here is what's called a Nakajima quiver variety. So, but we just convinced ourselves that this GIT quotient is exactly the same GIT quotient as Z chi stable by GLN. So what we've done is just found a slightly different construction of the Hilbert scheme of endpoints, namely as this Nakajima quiver variety. So what we were doing before, this simple, I claim, intuitive construction of the Hilbert scheme of endpoints, all along it was actually, or you can view it if you put on slightly different glasses, as a Nakajima quiver variety. And so we ask, so what? Who cares? And the point is we get something from this. This allows us this sheds an awful lot of light on the geometry of the Hilbert scheme. The point is that we know quite a lot about Nakajima quiver varieties. They satisfy many very nice properties, and one of which is this morphism obtained by variation of GIT quotient, that I had this, for this particular choice of character, I naturally admit a morphism to the space where I take the character 0. And in fact, this is just this affine GIT quotient. So this set is actually a spec of the coordinate ring of W that's invariant under GLN. So I've got a perfectly nice morphism from this Nakajima quiver variety to this affine variety. And if we apply the isomorphism from this space to the Hilbert scheme of endpoints that we've just seen, it turns out that we recover, we gain an awful lot of understanding of the Hilbert scheme of endpoints. In other words, there's an isomorphism from here to here, and moreover, this affine variety is something that we can understand because it's the nth symmetric product of the affine plane, or if you like, take n copies of the plane, K2 with itself, and then let the symmetric group act to permute those copies and look at the quotient, look at the orbit space. So this here is an orbifold. And not only is there a morphism, but it's one that we can analyze easily using some understanding of Nakajima quiver varieties. So this morphism, it's a projective crescent resolution of singularities. And this means in particular, this guy is smooth, though it's non-singular. It's got dimension 2n. Of course, it's clear that this space has dimension 2n, and it's got a trivial canonical class. So this is, if you like, a non-compact Calabi-Yau manifold of dimension 2n. Hal Schenk later on today will talk about Gorenstein affine varieties. So something's Gorenstein if its canonical class is trivial, and indeed this Crepin condition means that the canonical class is preserved. And so the Hilbert scheme of endpoints has trivial canonical class. This is one observation. Let's also say it's really, of course, a result of Grothendieck, but in this context I'm talking about Alastair King or Hiraku Nakajima. This particular construction endows the Hilbert scheme tautologically with a vector bundle whose fibers encode all these vector spaces we've been studying all throughout this talk. So suddenly we know an awful lot about the Hilbert scheme of endpoints in the plane. So I've got one more section, but I'm conscious. So I've gone to 11:35. I know I started a little later, and I think there's a few more pages where I say how one can extend this to say something that's new. So everything so far is very, it's written in books, it's expository, very well known. And I'll move on to say that some of what we've seen could be extended naturally from the plane to ADE singularities, but certainly not everything. So very briefly, what do I mean by an ADE singularity? So this is simple surface singularities, or ADE singularities are simply quotients of the affine plane by a finite subgroup of SL2. And famously, due to Duval in the 30s, I think, each of these affine surfaces can be realized as a hypersurface in free space. Armed with this well-known description, I want to construct for you the Hilbert scheme of endpoints on each ADE singularity K2 on gamma. And the idea is to take our first intuitive construction and do something very, very similar. I'm going to have I'm going to have B1, rather than just B1 and B2, I'm going to choose 3 matrices, but I'm going to insist that, yes, the BI's commute, or if these were arrows, that A1, A2, and A3, these arrows commute, I'm putting relations on the quiver, but I'm also putting a funny relation on. I'm going to use F gamma. It's a function of 3 variables, and I insist A1 and A2 and A3 commute, so I can define an equation involving, well, the arrows, or if you like, B1, B2, and B3. Oops, there we are. To introduce more complicated relations on this particular quiver. And with that, I go through exactly what we've seen before. I set up the space of all, well, now it's quadruples, but B1, B2, B3 with an I. I insist that the BI's commute and they satisfy this key defining equation. With that, I choose exactly the same character as before, and sure enough, the Hilbert scheme of endpoints, for exactly the same reasons as before, is the chi-stable locus in this set, or this affine scheme, modulo the action of GLN. So this gives us a GIT description of the Hilbert scheme of endpoints on an ADE singularity. And so to conclude, I'll say, well, the thing that allows us to probe the geometry for the Hilbert scheme of points in the plane was the fact that it was a Nakajima quiver variety. And it's natural to ask, can we do the same thing? If I add an extra arrow back here, do I get a Nakajima quiver variety? And this is obviously the wrong thing to do, simply by counting the number of arrows in the picture. So it turns out that it is nevertheless still possible to give a Nakajima quiver variety description of the Hilbert scheme of endpoints on an ADE singularity, but it is a good deal harder. And it's not simply a case of adding 1 arrow. What we want to do is use the Mackay quiver associated to the finite subgroup. So I'll move to the final slide where I'll say briefly, the Mackay quiver, so John Mackay in 1980 associated to this finite subgroup SL2 an affine Dynkin graph. So here's the D5 tilde case, and this is a graph, but let's build a quiver just by putting an arrow in each direction. So I've got a pair of arrows for every edge. So I'm building the Mackay graph. And for Mackay's construction, each vertex corresponds to an irreducible representation of gamma. I've indicated the trivial representation, and to write down the graph or the quiver I care about, I put an extra vertex, a framing vertex, and I put an arrow in each direction from that to the trivial representation. So I get a new quiver, and the goal is to study quiver varieties for this quiver. So now I've got lots of vertices, so the kind of characters we're choosing when I make GIT quotients, and the dimension vectors I'm choosing aren't just integers. There's something in with in the lattice of dimension, the number of vertices. But nevertheless, in this final result, actually, gosh, I should have said this is joint with Cern, Gamogo, Adam Dienga, and Bolash Sendroy in a paper from last year that was published this year, that there is a GIT description construction, at least for the Hilbert scheme of endpoints, if we take the reduced scheme structure for ADE singularities as a Nakajima quiver variety. We have to be careful about which character we choose. So I'm not telling you which character it is. It's a non-generic character. But the point then is that this morphism for Nakajima quiver varieties, which is given by variation of GIT, this is, well, previously for the plane, it was a Crepin resolution. Here it's a partial Crepin resolution. So this is singular. Even with a reduced structure, it's singular. But nevertheless, so it's a partial Crepin resolution, and this guy admits a unique projective Crepin resolution. In other words, there's some unique n chi prime. So there's a unique projective Crepin resolution that's also a Nakajima quiver variety. And so that's the setup where we have generalized the Hilbert scheme of endpoints in the affine plane to the Hilbert scheme of endpoints on any ADE singularity. And perhaps I'll stop there.
Amazing. Thanks very much, Alastair. So yeah, I'll pass the chairing back to Andre.
Okay, thanks very much. I think we probably have a few minutes for questions. Are there any questions?
Could I ask a question, Ali?
Sure.
I've always wondered, how much of this can be pushed to general finite groups as quotients of C, and how much of Claviaunus is really needed in this kind of story. Do you have any comments on, how can one, because you can construct Mukai quiver from just the group theory point of view for any finite group in any dimension.
So the first intuitive construction will go through verbatim.
I'm sorry, it will.
The first construction, this sort of simple construction,
Yeah.
just to get a GIT description, yeah, that'll go through verbatim. If you write down, whatever, it doesn't even have to be a hypersurface, right? Any defining equations for your singularity, you can have a collection of equations. You insist if they're in n variables, you put n arrows on, and you can do that and make that go through. So yes, that's a nice simple GIT description of the Hilbert scheme of endpoints. If you want a Nakajima quiver variety construction, then you're going to struggle because these are known to be, at least for dimension vectors where they're primitive, so indivisible vectors, and in particular, I was going to put dimension vector 1 at this vertex. Then for a generic parameter, they are crescent resolutions of the affine quotient. This being the case, whatever resolution, so if a similar story happens, so I should say the Hilbert scheme of endpoints, it's for a non-generic parameter. It's a very specific parameter in actually an intersection of many walls in the GIT chamber construction. So wherever you are, there will be a morphism from a crescent resolution to the Hilbert scheme of points, if indeed the same story generalizes. This then would make your Hilbert scheme of endpoints, this forces it to be a partial crescent resolution of the singularity, but it's not going to be the case for even the subgroup of GLN that's not SL, because even the Hilbert scheme of 1 point doesn't fit into that picture. So yes to the first simple intuitive geometric construction, but at least the naive generalization would one hope for a Nakajima quiver variety description? My initial thought is probably not.
So when you don't have crescent resolution, what do you get? Do you even get a variety from the naive generalization of Nakajima quiver?
In this setup, yes. So with this guy, you can always do, and you definitely get a variety. You get a perfectly nice scheme, a nice GIT description. But the question is, how then is there some nicer description that enables some of the point is that there's a tension here. There's a simple one, but that doesn't tell you very much, and it's the link to the Nakajima quiver variety from which we can learn a lot that enables us to draw interesting conclusions. And so I claim you do get the simple one, but it's not clear to me whether there's a deeper one where we can easily draw nice geometric conclusions in general.
Thank you.
Okay, well, thanks very much.